This is lesson 4.1 and 4.2 on slope and rate of change. This is the first lesson of chapter 4, which is on linear functions. This chapter builds on what we learned in the last chapter, chapter 3, which is about relations and functions. Those were more general relations and functions, whereas this chapter is specifically focused on functions that are linear, in other words, straight lines. Vocabulary recap from last year in Math 9, you should know what a linear equation is. This is an equation with two variables, usually x and y, and there's no exponents on the variables. And if you were to graph this, it's a straight line on a graph. So here's a couple examples of some linear equations. The signs can be positive or negative, but it's usually y equals something x plus something. New vocabulary this chapter is a linear function. So this is a linear equation that represents a function. Almost all linear equations are linear functions with the exception of vertical lines. We'll talk more about that in a bit, but a vertical line is not a function because it would fail VLT or the vertical line test at every single point. But all other straight lines are linear equations, which are also linear functions. A very important new vocabulary word is slope. We're going to use this a ton in chapter 4, 5, and 6. Slope represents the steepness and the direction of a line. So some examples here, this would represent a positive slope because it's going up to the right, and this is a fairly steep slope. Whereas this here is still a positive slope because it's going up to the right, but it's not as steep as the other line, so that would be like a moderate size slope. Both of these lines are negative slopes because they're going down to the right, and this first one is a little bit steeper than the second one. So positive slopes are when you go up to the right, negative slopes are when you go down to the right. And you can remember this a lot easier if you just think of all the times in your ordinary life that you see slope in the real world. So a hilly sidewalk, there's a lot of those in Vancouver, the mountains that you might ski or hike on, wheelchair ramps, stairs. We have a pretty good idea of when a slope is really steep, moderately steep, or flat. So for example, this could represent if you were hiking up a mountain because it's pretty steep. This could represent when you're skiing down a mountain. A completely flat line would maybe be if you were like walking down the hallway. And then you could have some smaller slopes if you were just walking out in the city. Slope is represented by the letter M, and it can be calculated on a graph by counting the distance between different points. So how much has the line traveled up or down, and how much has it traveled side to side? So these are the steps to find a slope from a graph. You just pick any 2 points on the line and count the vertical or horizontal difference between those 2 points. So as I said before, positive slope goes this way. So if you're traveling up, if there's any upward movement or any movement to the right, those are both positive changes. But if you have movement going down or movement to the left, then those are negative changes. This is our very important rise over run formula that we use to calculate the slope. And it's going to be how much the vertical changes divided by how much the horizontal changes. That's why we call it rise over run, because rising is like up and down movement, and running is our horizontal or side to side movement. So again, it doesn't matter which 2 points you pick, as long as in the end you fully reduce your fraction. When we do some examples, this will make more sense. So given this graph, we want to find the slope. We can pick any 2 points. Let's do the blue one first. If I pick those 2 points here, and I'm comparing going from this point up to the other point, how much has the graph risen and how much did we run side to side? So we only went up 1, but we moved to the right 2. And remember, upwards movement and right movement are considered positive changes. So those are both plus. So our slope, or our M, would be rise over run, which is 1 over 2. This is all you have to do. It's a fully reduced fraction, so you leave it as 1/2. We also could have predicted that this would be a positive slope because this line is going up to the right. But let's say you had picked 2 different points in the graph, because again, you can pick any 2 points. Maybe I picked these 2, and I was comparing from the first one here down to the other one. What change has occurred? We've gone down 1, so that's -1 movement. We've gone to the left 2, so that's -2 movement, because down and left are negatives. So maybe instead you had calculated your slope as -1 over -2, But once you've reduced the fraction, you get the same answer that you would have if you had picked a different set of points. The reason you can pick any points is because linear equations or linear functions have a consistent slope throughout the entire graph. They continue in that straight line forever. So it doesn't matter which ones you pick, you'll always get the same slope. It's always the same steepness. In this example B, we can predict that it will be a negative slope because it's going down to the right. And to calculate the exact slope, we just pick any 2 points. So I picked these two, and going from this point to this point, we've gone down 2 and to the right 3. So that would be -2 over +3, and that's fully reduced, so we're done. But let's say instead we had picked these 2 points a bit further apart, this one down to this one. We went to the right 6, so +6 movement, and we went down 4, so -4. So our rise over run would be -4 over 6, because the up and down movement always goes on top of the left to right movement. But you can't just leave your answer at -4 over 6. You have to reduce that fraction to -2 over 3, which now shows again that these two slopes are the same. It doesn't matter which 2 points you choose. There are some special cases of slope when you either have a horizontal line or a vertical line. So you can have a slope of 0 when you have a completely flat horizontal line. There's no incline at all. So that would be like this first example here. If you have a completely horizontal line, this has no steepness. It's not going up or down. It has a slope of 0. And that makes sense in the real world as well. Again, if you're walking down the hallway, it's going to be flat. You're not going up or down. There's no incline. So the slope is just 0. And I kind of prove this here using our slope formula. Rise over run, well, it doesn't even matter what our run is, how much you've gone left to right. The rise is 0. You haven't gone up or down. 0 divided by anything is just 0. So no matter what along this line, the slope is always 0. The other unique case is for vertical lines, and this has a slope that is undefined. It doesn't exist. And as we talked about before, it is not considered a function. It's the only straight line that's not a function because it fails the vertical line test. And what do we mean by undefined? If we try to do a rise over run formula, again, it doesn't matter what the rise is, how much you're going up or down. The run is always going to be 0 because you're not having any left or right movement. And you cannot divide anything by 0. No number is divisible by 0. If you tried this on your calculator, you would get an error message. So we just write it as an undefined slope. You could also think of it as like in the real world, you're not really ever interacting with slopes that are perfectly straight up and down. Like you would never be walking up a hill that has like at a 90-degree angle. You would never be walking up a hill that has a slope that is this steep. It would have like an infinite slope or undefined. So there's either 0 slope or undefined slope. Sometimes you want to calculate the slope even when you don't have a graph, if you just have points on the graph. And there's another equation here that we can use to calculate slope because you don't always have access to a graph. So if you're given 2 points, you again just calculate the difference in the y's divided by the difference in the x's. This is the same as our rise over run formula. It's the same idea. Because with the rise, we're just plugging in how much have the y's changed because that's up and down. And the run is how much have the x's changed because that's our side-to-side movement. So this is another formula that you need to memorize. The notation here is y2 and y1, x2 and x1. It just means if you have any 2 points, like the first one being labeled x1, y1, the second one being labeled x2, y2. That's what you would sub in here. So some examples. We have 2 points and we want to calculate the slope of the line that contains these 2 points. So I always find it helpful to label them as like x1, y1, x2, y2. It doesn't matter if you had flipped them, just label them and then you'll be able to sub them into your formula easily. So y2 minus y1 would be 4 minus 3. That's how much the vertical change has happened. And then x2 minus x1 would be 5 minus 1. And then we calculate that that would just give us 1 over 4. And you could always check this by graphing. Second example here, we have some negatives though, but same idea. It's helpful to label them as x1, y1, x2, y2, plug them into your formula, but always plug any negatives in with brackets, like what I've done for both of these things here, because in the next step, you can change that double negative to a positive. So it can get tricky when there's negatives, but if you always sub it in with brackets around it, you should be able to do that correctly because you'll notice that the double negative turns into a positive. This example here, I didn't label them this time, so you don't have to. You can just say, okay, what are the differences in the y's? Well, 4 minus 8 over 8 minus 10. What does that give me? It gives me -4 over -2. But make sure, again, you always fully reduce your fraction. This reduces to just +2. And then I've put a kind of side note here of another way you could have calculated it if you had switched which points were 1 or 2. If instead I had said 8 minus 4 over 10 minus 8, I would still get the same answer once I fully reduced the fraction. The only thing that you have to just make sure you, in terms of the order, you have to make sure you have is that um, the ones up and down have to be from the same point. So this 4 and 8 are both from this point, and this 8 and 10 are both from the other point. So those have to be lined up. Example D, once we plug this into the formula, we get 2 over 0. So this would be considered an undefined slope because it's a vertical line. And if you try to put that in your calculator, you would get an error message. And this is our other special case. Once we put these points into our formula, we get 0 over 3, which just gives us 0. Again, you can check that on your calculator. So we know that this is a horizontal line. To end off this lesson, we'll just talk about word problems, and this is where rate of change comes into play. Rate of change is just another word for slope. They are the exact same thing, slope and rate of change. If you think about what that means, it's like how much is something changing? What rate is something changing at? And the reason that like the place where we see this more often is in word problems, but you just calculate the rate of change the exact same way as you would calculate slope. When you come across problems for like find the rate of change from this graph, just calculate the slope. You might also see problems like this. Determine if each statement represents a positive, negative, or 0 rate of change. So you're taking context and trying to understand what slope would be existing from this context. So first example is if a graph represented the height of a baby from birth to age 3. This would be a positive slope because that child would be growing taller every year. So we want to apply that context to our knowledge of rate of change or slope. Second example, the elevation as you ski down a mountain, we can assume that would be negative because you're going down the mountain. Another example, the height of a human from age 30 to 40. This would probably be a 0 rate of change because you're not really growing when you're age 30 to 40. So your growing has stopped and it would be flat because your height is not changing. So that is our introduction to slope and rate of change, how we can calculate slope from a graph or from a set of points, and how we can understand rate of change in real world application.